Everyone, today we are going to solve LeetCode 3600, that is maximize spanning tree stability with upgrades. So the requirement for this problem will be what minimum spanning tree is and how do we implement it. So before we start, I will recommend you have revised what spanning tree is and how to implement using DSU. In case if you don't, I will explain it in simple terms, go over it, but feel free to have a look after this video is over. Yeah, so let's go over this problem, and it's a LeetCode hard problem, so it's one of those very good problem to revise your concepts. So you are given an integer n, and where n is the nodes, so we have nodes from, if there are n nodes, so 0 to n minus 1, and we are also given edges, where edges is of the form u of I, v of I, s of I, and must of I. So where u of I to v of I represents there is an edge with a strength of I, and must of I represents whether we need to take this edge necessarily or not. So must of I being 0 means we have an option to include this in our tree, spanning tree, or not. But if the must of I is 1, then we'll have to take this in our spanning tree. This edge cannot be, and also for those which must of I is 1, those edges can't be updated. So yeah, we also given something called k, integer k, where k is the maximum number of edges that we can upgrade, and we can only upgrade those edges where must of I is 0. So yeah, and the stability of spanning tree is defined as the minimum strength among all the edges. So the final answer that we have from the spanning tree, in that spanning tree, whatever is the minimum edge strength, post all these things operations have been done, that is the answer. And we need to record the maximum spanning tree stability, and if it is impossible, in that cases we return 1. So yeah, even here it's given what is a spanning tree is. A spanning tree is a graph, like, okay, so if there are n nodes, so it will have n minus 1 edges, and the graph is connected. Okay, so this is one other characteristics of spanning tree. Also there won't be any cycle. Okay, so that's what explained here. So let's go over the example. Here it's the sample. So n is 3 and edges is like of this form.
Into the problem statement with the example that we have till now. Okay, so let me see this. Okay, so we have this n is 3 and we have this 0. Let me draw the edges first, 0, 1 and 2. Now if you see these edges, so edges will be of the format u of I, v of I, and then strength of I, and then must of I, right. Now let's see. So 0 to 1, it says there's an edge with the strength 2. And is it required? Is it a must node? Yes, it's a must node, so I'll mark it as a tick. Now 1 to 2, it says the strength is 3. And is it a must node? No, it's not a must node. And k is 1, so that means I can upgrade one of the edge at this. So the only option left for me will be to upgrade this edge, because I can't upgrade an edge which is must. Okay, so for MST, right, if you want, so we have minimum spanning tree. Now we want maximum, so there's a slight modification in this. So the only modification that I will do in, like, when we implement this spanning tree, when we take the node and form the spanning tree, in that case I will take maximum priority queue instead of the minimum priority queue that you usually take in Cruscals or like whatever algo that we take. No, but don't worry, I will have your complete walkthrough of how the code is working and where the changes have done, right? So continue with me and you will understand. Okay, so for this, if I say, so okay, so for this, so what will be the edge? So this edge is required, and if you want minimum spanning tree, there are 3 nodes, so there must be 2 edges, so this edge is also required. So what will be my initial thinking on how this so let's understand how this is. So for this example, this is there and this is there, and we'll upgrade this edge, so it will become 3 into 2, there's 1, so it becomes 6, and minimum of this entire spanning tree, the minimum strength is 2, so the answer is 2. Now let me jump to this problem statement. Okay, so this is one thing. So we have 0, we have 1, 0 to 1, there is a strength of 4. Is it a required node? No. 1 to 2, it has a strength of 3. Is it required? Near. So now 0 to 2, and it has how much? So it has a strength of 1. Is it required? No. Okay, so so how will my final answer be? So I need so in my spanning tree I will have this node and this node, this sorry, edges, and this edge I will remove. Okay, So this edge will be removed, and don't worry how we remove and what are the logics that I will explain. I'm just explaining the example. So what will be the answer? So if you see, right, so this is the answer, right? And now since there are two edges, I have k equals to 2, I can upgrade any of the two edges, so I'll upgrade it, so it becomes 8, and if I upgrade it, it becomes 6. And if you see the minimum of 6 and 8, it's 6, so that's how is the answer. Now if you see this example, right, so it has 0, it has 1, it has 2. Okay, and the strength is 1. Is it a required node? Yes. Required edge? Yep. Is it a required? Is it required? Yes. And 1 to 2, let's see, the edge's strength is 1 and the required, again it has edge strength of 1 and it's required. Now a spanning tree cannot have cycles, right? But in case here, if you see, we need every edge to be taken into the solution that we're forming, right? And that violates the law of spanning tree that I've discussed above here, right? That you can't have a cycle, this, it should not have a cycle. So that's the reason why it can't have an answer, and that's how we're returning 1. So let's look at the constraint. The number of nodes is 10 to the power 5, and the edge length will be 10 to the power 5, of course. Okay, and edge format that is given to us, u of I, and it's also given that there's no duplicate edge. So k is also less than number of nodes, so you can't upgrade more than the number of nodes that we have. You can't, of course, update more than the edges. Okay, and must of I is this 0 to 1 boolean. I've already informed. So okay, so let's deep dive and how my thinking will be for this problem, right? So uh, let's start with our approach. Okay, am I gonna approach this problem? Okay, so let me see. I have this, and I have this, and okay, now let's see this, and this. Okay, and this is required. So the thing is, the first thing is, if you note from the problem, right, it is written that for those edges where must of I is 1, right, where must of I is 1, we have to take this edge. There's no exception. Take it compulsory, right? Pardon if it's wrong, the spelling. Okay, if it's take it, it's compulsory, right? For those edges where must of I is 0, we have an option. Either we take it or we don't take it. Take or not take, or not. But it's not TP problem, so don't go with this word like take, not take. So it's a knapsack, so it's not that. Okay, so let's go now. Let's say this is 0, 1, and this is 2. Okay, so how am I thinking to approach this problem, right? And let's say it's 3, and I have this, and okay, so let the strength be something like 2. Let the strength be 3, let the strength be 4, let the strength be 1. Okay, and this is a must node, this is must, and rest all are not must. So, and we have k is equals to, we can upgrade any of the one node. Okay, so what my solution will be, like since I need to form MST, right? So let me first go ahead and draw this. Right now I will take all the edges which are compulsory for me, right? So this edge is a necessary node for me. I can't skip this, so I will take this. So I'll make it 0, 1, 2, and 3. So I will have to take this irrespective of whatever is the edge strength. Okay, so this I have to take. Now do I need to take which out of this, which one do I take and which one I don't take? Okay, so what my approach will be, I will first start with the maximum edge strength. I will start, okay, I'll start with this. So I have to connect, so I'll start with this. So 4, that this represent edge and edge strength, and what is the edge that is connecting 0 to 2, and then I have 3, it represent 1 to 2, and then I have a strength of 1, and it is connecting 2 to 3. Okay, so I'll start with this one first. I'll see, can I take this edge, and how can you take a edge or not? So if connecting those edges, it's not forming a cycle, or not forming a cycle means, not saying not forming a cycle, but it doesn't belong to same component. Like if you see this and this are different components, right? Different component of the graph right now, so we can connect them if they are not forming. So okay, I can connect this, because if you see 0 and 2, they are two separate components, and if I connect it, it's not an issue for us. So I will take this. Okay, now let's see if I go to this one 3 2, can I connect this two? If I see 1 and 2, they are belonging to the same component, so I won't consider this. So this one I will take, so I won't take this edge because connecting it will form a cycle, and this anyway, this all were connected, so that doesn't make any sense to take this edge, so I will not take this. Can I take this one with the strength of 1, this one you mean? Yeah, so 2 and 3 belong to different components, and if you take this, it can be done. Okay, now, so so this is the final result that we will have, right? So this is the final graph that we have, resulting graph. Now, how do we find the answer, right? So there's one thing, now we have k is equals to 1, so we can upgrade any of the one edge, and we can upgrade only those edge which is not a necessary edge, where must of I is 0. So we can't upgrade this node, this edge, we can't upgrade this edge because it's a necessary edge, because must of I for this edge was 1. So we can either upgrade this edge or we can either upgrade this one edge. Which one do we upgrade? So what my thinking will be, so I will sort it whichever I need. So 1 and 4, these are the two edges that I have, right? And which one do I upgrade? So if I need to make the value, um, we know stability is given as minimum. Stability is minimum across all the edges, minimum across all edge strength, right? And now we don't have power for this, so this two we can't do anything. Now if I upgrade this, so it will become, there are two ways, like it will become 2 and 4, but if I upgrade this 4, it will become 1 and 8. And we already have, we know that we have to take this 2, right? So we have to take this 2. For this one the answer will be 1 because minimum is 1, so answer is 1. And for this case the answer is 2. And you know, the our job was to maximize the answer, so this is the answer. So what I got to know is, like, I will upgrade those which are less, right? So if I have k equals to 2, if I have k equals to 2 and I have uh, 3 to upgrade, right? A, B, C, D or E. So I will pick the first 3, like this should be sorted in the ascending order. So this will be, I will pick all those 2, like this 2, and I will upgrade them given it's sorted in ascending order. And what my answer will be, like, once this is done, I will pick the minimum across all this, so it will become 2A, 2B, and this, and max minimum across those that I have to take. So that will be my answer. Okay, don't worry, I'll explain all this. So my answer will be, so required one is 2, required is 2, I can't skip this one, right? And non-required is 1 and 4, and I already tell this will be sorted in ascending order. This I will push into a vector or something so that I can keep a track, like which all. So this, and I have k equals to 1, so I will upgrade this, like go over this and upgrade this, so it will become 2 and 4, and my answer will be minimum of this and this. So my answer is minimum this, so which is answer is equals to 2. So this is my approach. That's how I'll approach this problem. Okay, so now let's go into the code part. If you need the code part, I'm going to have the DSU template pasted in the comment section where you can copy it from in case if you want. And it is a GitHub repo link where I have many other segments or templates for the that you need for standard DSA or programming context. So feel free to have a look at that, and let's go. So now let's move back to my laptop where I will be coding the solution out, or I will just go through the solution out. Okay, so now we are back to this coding screen where I will implement the solution. Okay, so let me go through this solution that I have coded a debug. Okay, okay, so this is the DSU class which I have copied from my template, and I hope you know what DSU is. In case if you don't, please have a look at it. Yeah, so this is the standard template that I have copied from my GitHub. This is my repo, Striver SDSU, where you can find other templates as well. So feel free to have a look, and now let's go to the solution. Okay, so this is the standard template I have copied, which is DSU by rank. I usually use the DSU by rank more of the time. Okay, so now let's implement the solution. Okay, so what I'm going to do is I'll have this DSU. I'll implement get a DSU of size n plus 1. Now I'll have a priority queue. Okay, so in those cases where I will iterate over all the edges, right? As I mentioned, in each case the edges are required. So if the edges are required, so this is the I'm iterating over the edges, and in case the edges are required, then I will see what is the parent and what is the parent of node u and v. If the parents are same, right? In case in that means like the third case, right? That means we can't join this node, because it means there will be cycle, and all the and it's since it's required, that means we need to take it. So we'll return one that it's not possible. Else what we're going to do is we'll union this node, and we'll push this in the required. So I'm maintaining two vector which is required and not required, so that in our graph, so the final graph that we have formed, right, in those, like, this represent required represent the must take, and not required represent those nodes which didn't have, which we had an option and we took or not took. So okay, so this will push, and else if it's a not required, then we'll push in the priority queue, and this priority queue will be just as I mentioned, it will be ordered in the maximum to minimum form. That is, those which have the maximum strength, that will be in the top, and those we have the minimum will be in the bottom. So now we'll iterate over the priority queue. Okay, I'll iterate over the priority queue, and in this I'll pop out the top of the priority queue, and I'll find out what is the top, what is the nodes, okay, what is the strength and what is the nodes, and I will find if those two can be connected or not. If they have the same parent, right? DSU dot find parent. If they have the same parent, that means they can't be connected. So we'll continue. Else, what I'm gonna do is we'll push it into the not required one. Like, this was a not required. We had an option to take. Like, yeah, we'll store in that list. Like, we had an option to take, and in that we pushed back this S. Okay, and we'll merge this DSU. So once this is done, what we have a list. So we have a list right now with the edge strength, right? Where required says, like, uh, required means must is equals to 1. Edge, for that edge the must was 1, and the list will be strength I, and that will be going like this. Okay, uh, and the second one is not required, so that will be must is equals to 0, and we had an option, so we had an option to choose or not choose, and we took all those. So we also have the strength j and j0, strength j1, like that. Okay, so now let's move to the next part. So we had a strength take or not take, and what we did is we sorted it, right? As I mentioned, we need to sort it, right? We had sorted it. Now once that sorting is done, what I'm going to do is I will first find, like, uh, is the cycle connected or not, is the graph connected or not, the final result that we have formed till now, that till here, is the graph connected or not. So how do we check if a graph is connected or not? So if all the nodes have the same parent, that means the graph is connected, else the graph is not connected. And in case if the graph is not connected, in that case it's not a spanning tree, right? So I'll return -1. And now I'll just go ahead and find the answer. So since I've already sorted the required as well as the not required one, so we know initially answer we are making it integer max. Okay, now we know the required size. If the required had some node, if there was some edge that was required, so answer will be the minimum of the required. Okay, so we took answer as the minimum of the required of 0, and we iterate over the not required. So for the not required, let's say we have some format, right? So we iterate over this not required edges, and we multiply it by 2. So maximum we can go up to k, and that's why we are doing minimum of k and whatever the size. So max we can go is k size. So and then we'll sort it, and once it's sorted, the answer will be minimum of uh, answer, that is the required one front and the not required one 0, and at the end we'll return the answer. So that was it. The implementation was not a very hard, but yeah, it has a good problem concept.